Hello friends, welcome to my lecture on exponential distribution. Let NT be a Poisson process with rate lambda. Let x1 be the time of first arrival, okay. Then P, the probability that x1 is greater than t, will be equal to probability that there is no arrival in the interval 0 to t, because x1 is the time of the first arrival and x1 is greater than t. So, in the time interval 0 to t there will be no arrival, and probability that there is no arrival in 0 t means probability that nt equal to 0, okay. Nt equal to 0 means we have probability of, in a Poisson process, probability that nt is equal to n is equal to lambda t raised to the power n e to the power minus lambda t divided by n factorial. So, there is no arrival in 0 t means probability that nt equal to 0. Nt equal to 0 means lambda t to the power 0, which is 1, then e to the power minus lambda t divided by 0 factorial. So, this will be e to the power minus lambda t. So, this probability of no arrival in 0 t is actually probability of nt equal to 0. Okay, there is no occurrence in the time interval 0 to t. Okay. So, this is equal to e to the power minus lambda t, hence fx1 t. Fx1 t is probability that x1 is less than or equal to t. Okay. Probability that x1 is less than or equal to t, and this is equal to 1 minus probability that x1 is greater than t. Okay. So, probability that x1 is greater than t is e to the power minus lambda t. So, this would be 1 minus e to the power minus lambda t. So, we will get this 1 minus e to the power minus lambda t when t is greater than 0, and it will be 0 otherwise. Okay. Now, therefore, x1 is an exponential lambda distribution. Okay. X1 is an exponential lambda distribution. Okay. So, x1 is exponential lambda distribution. Let x2 be the time elapsed between the first and second arrival. Okay. So, x1 is the time of the first arrival, x2 is the time elapsed between the first and the second arrival. Okay. So, then x3 is the time between the second and third arrival, like that. Okay. So, what we have, let s be greater than 0 and t be greater than 0. Let us note that the two intervals 0s and s plus t are independent. We know that the number of occurrences are independent of the non-overlapping intervals. If there are two intervals which are non-overlapping, number of occurrences in one is independent of the number of occurrences in the other. So, let us note that 0s and s plus t are independent. Therefore, probability that x2 is greater than t given that x1 equal to s. Okay. Given that x1 equal to x1 is the time of the first arrival. Okay. So, x1 is equal to s, that means s is the time of the first arrival. X2 is greater than t means there is no arrival, okay, in s plus t. Okay. x2 is the time elapsed between the first arrival and the second arrival. First arrival occurs at s, okay, at time s. Okay. So, that means, and the time elapsed between the first arrival and second arrival is more than t, it will mean that there is no arrival in the interval s plus t, okay, given that x1 is equal to s. Now, s plus t and 0s are independent. So, probability that no arrival is there in s plus t interval given that x1 equal to s is same as probability that there is no arrival in the interval s plus t. Okay. Now, there is no arrival in s plus t is same as the probability that there is no arrival in the interval 0 to t. Okay. We have already found the probability of no arrival in 0 t. Probability of no arrival in 0 t, okay, is same as probability of no arrival, because it follows the same probability distribution. So, no arrival in s plus t means e to the power minus lambda t. Okay. It follows the same probability distribution means no arrival in s plus t will mean that probability that nt equal to 0. Okay. So, this is the number of occurrences in the time interval 0 to t. Okay. Because of the independence of 0 to t and s plus t, number of no occurrences in the interval s to s plus t will be no occurrence in the interval 0 to t. So, that is probability of n t equal to 0 we can find. So, this will be lambda t to the power 0 e to the power minus lambda t divided by 0 factorial. So, this is e to the power minus lambda t. So, we get the probability of x 2 greater than t given that x 1 is equal to s as e to the power minus lambda t, and thus we can conclude that x 2 is exponential lambda follows exponential lambda distribution. Thus, x 1 and x 2 are we conclude that x 2 follows the exponential lambda distribution and that x 1 and x 2 are independent. The random variables x 1 x 2 are called inter-arrival times of the counting process. As we have seen that x 1 is the time of the first arrival, x 2 is the time elapsed between the first and second arrival, x 3 is the time elapsed between second and third arrival. So, they are called inter-arrival times of the counting process n t. Similarly, we can argue that all xi's are independent and xi's follow exponential lambda distribution. Now, inter-arrival times for Poisson process. If n t is a Poisson process with the rate lambda, then inter-arrival times x 1 x 2 are independent and follow exponential lambda distribution. Okay. If x is exponential with parameter lambda greater than 0, then x is a memoryless random variable. Okay. So, x is a memoryless random variable means the probability that x is greater than x plus a given that x is greater than a is same as the probability that x greater than x. Okay. So, whatever has happened given that x greater than a means whatever has happened for x greater than a will not affect the probability that x is greater than x plus a. It only depends on the length of a to x plus a, that is x. So, probability that x is greater than x, later we shall in the lecture we shall discuss in detail about this memoryless property of the exponential distribution. So, we will see that it depends on the length of the interval, not on the values of this a and x plus a. It only depends on the length of the interval. Now, let us define the random variable t as the waiting time. Let us define the random variable t as the waiting time for the first occurrence from time t equal to 0. Okay. So, t is the waiting time for the first occurrence. Okay, from time t equal to 0, then t is a continuous random variable since it can take any value in an interval. The distribution function of the random variable t is obtained by relating it with the discrete random variable n t. We know that n t is a discrete random variable of a continuous variable t, and n t denotes the number of occurrences in the interval 0 t. Okay. The event t greater than t is the same as the event n t equal to 0, because t is the time of the first waiting time for the first occurrence, and if t is greater than t, it is same as n t equal to 0. There is no occurrence in the interval 0 to t. Now, recall that n t is a discrete random variable with Poisson distribution with parameter lambda t. This we have discussed in the previous lecture, that n t is a discrete random variable and follows Poisson distribution with parameter lambda t, because the probability here in is given by lambda t raised to the power n, probability that n t equal to n is equal to lambda t to the power n e to the power minus lambda t divided by n factorial. Okay. So, it follows a Poisson distribution with parameter lambda t. Probability that t is greater than t is same as we have just now discussed. T is the time elapsed between t equal to 0 to t for the first occurrence. Okay. So, if the time for the first occurrence is t and it is greater than t, that means in the interval 0 to t there is no occurrence. So, probability that n t equal to 0, n t equal to probability of n t equal to 0 is e to the power minus lambda t to the power 0 over 0 factorial. So, it is e to the power minus lambda t. Thus, probability of t less than or equal to t, probability that t is less than or equal to t is 1 minus probability that t is greater than t. Okay. That is, it is 1 minus e to the power minus lambda t, t greater than 0. Hence, the distribution function of t is given by, because f t t denotes the distribution function of t. Okay. So, it is given by probability that t is less than or equal to t. Okay. And we have seen probability of t less than or equal to t is 1 minus e to the power minus lambda t. Okay. So, the distribution function of t is given by FTT and it is equal to 1 minus e to the power minus lambda t. Now, this distribution function of t is referred to as the exponential distribution. Thus, we can conclude that the waiting time for the first occurrence, okay, in a Poisson process, okay, is distributed in the exponential form. Okay. It is given by 1 minus e to the power minus lambda t. Now, the probability density function of t, we know that the derivative of the distribution function FTT, the cumulative distribution function gives the probability density function. So, probability density function if we denote by FTT, it is d over dt of FTT, okay, and d over dt of FTT we can find from here. FTT is equal to this one 1 minus e to the power minus lambda t, okay, when the t is greater than 0 and 0 otherwise. Okay. So, from here d over dt of FTT we can determine this is equal to lambda e to the power minus lambda t, okay, when t is greater than 0 and 0 otherwise. Okay. So, as we have just now seen probability density function, okay, probability density function is equal to derivative of the distribution function. Okay. So, probability density function of the exponential distribution is given by FTT equal to lambda e to the power minus lambda t when t is positive and 0 otherwise. Okay. So, we get this. Now, this is the probability density function of the exponential distribution with parameter lambda greater than 0 for t greater than 0. FTT if you integrate, okay, FTT equal to this, we earlier also we discussed this FTT, when you integrate this equation FTT is given by integral over minus infinity to t FTX dx. Okay. So, the CDF, the cumulative distribution function of t, okay, the random variable t is given by integral over minus infinity to t FTX dx. Okay. And here you can easily see that if you put the value of FTX, okay, FTX is equal to 0 when x is less than or equal to 0. Okay. So, from here we can see this is equal to integral over 0 to t FTX will be equal to lambda e to the power minus lambda x dx, okay, if t is greater than 0. If t is less than 0, then FTX will be 0. So, this cumulative distribution function FTT equal to 0, and when you integrate this, what we get is e to the power minus lambda x divided by minus lambda multiplied by this lambda, and we take 0 to t. So, this gives you when you can cancel this lambda with this lambda, and when you substitute the limits you get 1 minus e to the power minus lambda t. So, FTT equal to 1 minus e to the power minus lambda t when t is greater than 0, okay, and 0 otherwise. Okay. So, we get back the cumulative distribution function FTT. So, FTT is equal to integral over minus infinity to t FTX dx. Okay. Now, here you can see the graph of this is the graph of density function, okay, FTT, and this is the graph of, we have taken FTT, here we are taking CDF. Okay. So, you can see FTT is given by lambda e to the power minus lambda t when t is greater than 0 and 0 when t is less than or equal to 0. This means that limit t tends to 0 minus FTT equal to 0, okay, and limit t tends to 0 plus FTT is equal to when t goes to 0, e to power minus lambda t goes to 1. So, this goes to lambda. Okay. So, the value of FTT at t equal to 0 is 0. Okay. So, the value of FTT at t equal to 0 is 0. So, the 0 point is here. Okay. This means that and lambda is, we have taken lambda to be positive. So, since lambda is greater than 0, okay, FTT is discontinuous at t equal to 0. Left and right hand limits are not same. You can see the graph also, okay, when t tends to 0 plus, it goes to the value lambda. This is lambda here, okay, and on the left side, okay, on the negative t axis, FTT is everywhere 0. So, it is continuous on the whole t axis except at t equal to 0, while the function FTT, okay, FTT is continuous on the for all values of t. FTT is equal to 1 minus e to power minus lambda t when t is greater than 0. We can find the limit here as t tends to 0 plus. So, when t goes to 0 plus e to power minus lambda t goes to 1. So, 1 minus 1 is 0, this means 0 we get, and limit t tends to 0 minus FTT is also 0. Okay, and at t equal to 0 also it is 0. Okay. So, FT0 is also 0. Okay. So, we have FTT is continuous for all t. Okay. So, this is clear from the graph also. Okay. On the negative t axis, FTT takes 0 value for all t. Now, so density function of the exponential distribution, that is FTT, okay, FTT, this is continuous everywhere except at t equal to 0. Okay. The distribution function FTT is, however, continuous everywhere. Now, the exponential distribution is used in life testing, reliability, queuing theory, and many other areas. Okay. Life of an electronic fuse, okay, or equipment which does not age with time. Okay. Service time for a customer in a facility, waiting time between two occurrences of a Poisson process are some of the examples of exponential random variable. Now, let us take some examples. Suppose we have to find when we have to solve this problem, the number of miles that a particular car can run before its battery wears out is exponentially distributed with mean with average of 10,000 miles. So, the owner of car needs to take 5,000 miles trip. Okay. What is the probability he will be able to complete the trip without having to replace the car battery? Okay. So, here we are given mean of the exponential distribution. Mean of the exponential distribution, and mean is given by 1 by lambda. Mean is equal to 1 by lambda. Mean of the exponential distribution is equal to 1 by lambda. So, 1 by lambda is equal to 10,000 miles, okay, which implies that lambda is equal to 1 by 10,000. Now, the owner of car needs to take a 5,000 miles trip. What is the probability he will be able to complete the trip without having to replace the car battery? So, let us say let x denote the number of miles the car can run before its battery wears out. Okay. Then we want the probability that x is more than 5,000. If x is more than 5,000, he will be able to complete the trip without the battery wearing out. So, this is equal to integral over 5000 to infinity, okay, the FTT, okay. FTT means lambda e to the power minus lambda t dt, okay. That is the probability density function of the exponential distribution. So, lambda is equal to 1 by 10,000 integral over 5000 to infinity e to the power minus lambda t. So, this is equal to 1 over 10,000 e to the power minus lambda t divided by minus lambda, and we have 5000 to infinity. Okay. Now, when t goes to infinity, lambda is greater than 0, lambda is 1 by 10,000. So, e to power minus lambda t will go to 0, and therefore, this is 1 by 10,000, and when it is 5000, okay, then but we will get e to the power minus 5000 lambda divided by lambda, okay, we will get this. Okay. Now, lambda is 1 by 10,000. So, this lambda and this 10,000 will cancel, okay, and what we get e to the power minus 5000 lambda. So, this is equal to e to the power minus 5000 into 1 by 10,000, and this is equal to e to the power minus half, okay. E to the power minus half comes out to be 0.604. So, he will be able to complete the probability trip with the probability of 0.605. That means, there are more than about 60% chance that he will be able to complete the trip without the battery wearing out. Now, let us go to next question. Suppose the length of a phone call in minutes follows the exponential distribution with parameter lambda equal to 0.1. If someone arrives immediately ahead of you at a public telephone booth, find the probability that you will have to wait more than 10 minutes. So, let x denote the waiting time . Okay. Waiting time for a phone call . Okay. So, then we want the probability that we have to wait more than 10 minutes, that is x is greater than 10. Okay. So, this will be integral 10 to infinity, okay, lambda e to the power minus lambda t dt, and lambda is equal to 0.1. Okay. So, this we can write lambda here, and then 10 to infinity e to the power minus lambda t. So, integral will be e to the power minus lambda t divided by minus lambda, and we have this situation. This will be equal to, this lambda will cancel with this lambda, and we will have, when t goes to infinity, e to the power minus lambda t will go to 0, and when it is 10, it will be e to the power minus 10 lambda. Lambda is 0.1. Okay. So, e to the power minus 10 into 0.1, which means e to the power minus 1. So, we will have to wait more than 10 minutes. The probability will be e to the power minus 1. Okay. Now, we have to wait between 10 and 20 minutes. So, probability that 10 is less than x less than 20. Okay. So, this means we need the probability, that means we have to calculate the integral 0 to 10 to 20 lambda e to the power minus lambda t dt. Probability that a is less than x less than b is given by integral over a to b f t t dt, that is the density function. Okay. So, we have here e to the power minus lambda t divided by minus lambda into lambda, and we have 10 to 20. Okay. So, this lambda will cancel with this, we will get e to the power 10 lambda minus e to the power minus 10 lambda minus 20 lambda, okay, when we should put the limits. Okay. So, this is e to the power minus 1 minus e to the power minus 2, as lambda is equal to 0.1. Okay. So, we get this probability, and this is the probability that we have to wait between 10 and 20 minutes to make the call. Okay. Now, suppose we have this problem, students arrive at a local war and restaurant according to an approximation Poisson process at a mean rate of 30 students per hour. What is the probability that the bouncer has to wait more than 3 minutes to card the next student? So, students arrive at a local war and restaurant according to an approximate Poisson process at a mean rate of 30 students per hour, meaning that the Poisson mean is 30 by 60, okay, 30 student per hour means half student per minute. Okay. Now, let us say let W denote the waiting time okay, then we can expect on an average two minutes waiting time between arriving students. Because we have got half student per minute means in 2 minutes one student. So, there will be we can expect that there will be a time interval of 2 minutes between arriving students. So, we want that we want the probability that the bouncer has to wait more than 3 minutes. Okay. On average the time is 2 minutes between arriving students, but we want the probability that the time when waiting time is more than 3 minutes. So, we want the probability that the waiting time is W is more than 3. Okay. That means integral 3 to infinity lambda e to the power minus lambda t dt. Okay. Now, as I said, mean of the exponential distribution is 1 by lambda. Okay. Now, on an average what we are getting is the waiting time is 2 minutes. Okay. Waiting time is 2 minutes. Okay. So, 1 by lambda equal to 2 minutes, that means lambda equal to 1 by 2. Okay. This lambda is same as the mean of the Poisson process, the same lambda. So, lambda is equal to half. So, 1 by 2 integral 3 to infinity okay, e to the power minus t by 2 dt, because lambda is equal to half. Okay. So, we have 1 by 2 e to the power minus t by 2 divided by minus half. This will cancel with this and we get what? When t goes to infinity it will go to 0. Okay. So, we get e to the power minus 3 by 2. e to the power minus 3 by 2 is 0.223. So, the bouncer will have to wait more than 3 minutes, the probability for that is 0.223. Okay. Now, the expectation and variance of exponential distribution. The service time t for a customer follows the exponential distribution with parameter lambda. So, here et is the expected time of t, expected time of t is equal to minus infinity to infinity, as we have written here, t times the density function f t t dt. Okay. This integral over 0 to infinity, because f t t the density function f t t it assumes value 0 when t is less than 0. So, this is 0 to infinity okay, t times lambda e to the power minus lambda t dt. Okay. Now, take lambda t equal to u, then lambda dt is equal to du. Okay. So, what do we get here? And the limits, because lambda is greater than 0, as lambda is greater than 0, okay, when t goes to infinity u goes to infinity, and when t is 0 u is 0. Okay. So, the limits do not change. Okay. For t we put u by lambda okay, and lambda dt we replace by du. So, we have e to the power minus u du. Okay. Now, this is 1 by lambda. So, we have 0 to infinity u e to the power minus u du. Okay. Now, we can integrate by parts. So, we get 1 by lambda u times minus e to the power minus u, 0 to infinity, and minus derivative of u is 1, then we have minus e to the power minus u du. Okay, so, this will be now when u goes to infinity, okay, u times e to the power minus u goes to 0. Okay. So, we have this 0, and then when we put 0 here for u, we get this 0. Okay. So, what we get ultimately 1 by lambda and minus minus becomes plus. So, 0 to infinity e to the power minus u du, and this is 1 by lambda, we have e to the power minus u minus sign. Okay. 0 to infinity. So, when u goes to infinity it is 0, when u is equal to 0 it is 1. So, with minus and minus we will put because of lower limit. So, we will get it as 1 by lambda, and we get 1 by lambda as the mean of the exponential distribution. Okay. In order to determine variance of t, we need to determine E t square. E t square is integral over minus infinity to infinity t square f t t dt. Okay. And this we can similarly determine as we have determined E t. Okay. So, this will be f t t is again 0 when t is less than 0. So, we can put it as integral 0 to infinity t square f t t will be lambda e to the power minus lambda t when t is positive. Okay. So, we can put again lambda t equal to u. Okay. This will be equal to, putting lambda t equal to u, this will be equal to integral 0 to infinity t square will be u square by lambda square, okay, into lambda dt will be du. So, u to the power minus u du, where lambda t equal to u. Okay. So, this will be 1 by lambda square integral 0 to infinity u square into e to the power minus u. So, because of u square here, you have to integrate it twice with respect by integrating by parts, and you will see that its value comes out to be 2. Okay. So, 2 by lambda square we get. Okay. So, we get this 2 by lambda square. Variance of t is then E t square minus E t whole square. Okay. So, that is 2 by lambda square, E t square means 1 by lambda square. So, we get the variance as 1 by lambda square. Okay. So, variance is 1 by lambda square and mean is 1 by lambda. Okay. So, mean is 1 by lambda, we will use in the examples. Now, let us discuss memoryless property. The the exponential distribution has a characteristic property. Okay. There is a characteristic property of the exponential distribution. It is called lack of memory property. Okay. Suppose x denotes the length of life of an electronic fuse. Okay. Length of life of an electronic fuse. Further, suppose that it is known that fuse has already lasted t naught units of time. What is the probability that it will fail before t units, t greater than t naught? Then the required probability is p x less than or equal to t. Okay. X denotes the length of life of an electronic fuse. So, we want the probability that it fails before t units of time. So, x must be less than or equal to t, but given that it has already lasted t naught units of time. So, x is greater than or equal to t naught. Now, this is conditional probability. Okay. Probability that x is less than or equal to t given that x is greater than or equal to t. We know that probability of A given B is equal to probability of A intersection B divided by probability of B. Okay. So, using that we will have, this is event A, this is event B. Okay. Intersection of A and B will be t naught less than or equal to x less than or equal to t naught less than or equal to x less than or equal to t. Okay. So, we will have the probability that t naught is less than or equal to x less than or equal to t divided by p x greater than or equal to t naught. Okay. Now, so this new in the numerator what we will have integral T naught to T and then the probability density function of the exponential distribution, which is lambda e to the power minus lambda x. Okay. So, lambda e to the power minus lambda x dx, and the denominator will be, we have to find the probability that x is greater than or equal to T naught. So, T naught is equal to infinity lambda e to the power minus lambda x dx. When we integrate this, what we get e to the power minus e to the power minus lambda x we get. Okay. And the limits are T naught to T divided by e. Here we have again have minus e to the power minus lambda x, the limits are T naught to infinity. Okay. So, numerator will be e to the power minus lambda T naught minus e to the power minus lambda t, and denominator, because x is lambda is positive, x when goes to infinity it will go to 0, e to the power minus lambda x will go to 0. So, it will be e to the power minus lambda T naught. So, we get this, okay, and this we can write as 1 minus e to the power minus lambda times t minus T naught. Okay. Now, you can see the probability that the length of life of the electronic fuse, okay, will be at most t units, okay, given that it has already lasted T naught units of time, is depends on the length of time t minus T naught. Okay. It depends on the length t minus T naught. Okay. So, what we have, this property depends only on this length t minus T naught and not on the location of T naught. Hence, the probability that the electronic fuse will fail in the next 5 minutes, given that it has already lasted 10,000 hours, is the same as the probability that the electronic fuse will fail in the next 5 minutes, given that it has lasted only 1 hour. Okay. So, suppose the electronic fuse has already lasted 1 hour, and we have to find the probability that it will fail in the next 5 minutes. That probability is same as the probability that it has already lasted 10,000 hours and it will fail in next 5 minutes. Okay. So, this is called the memoryless property. The probability does not depend on what has happened before t naught units of time, it only depends on the length t minus T naught. Okay. So, this is called the memoryless property of the exponential distribution. So, that is all in this lecture. I thank you very much for your attention.